So let's contrast verification to learning, just to be explicit. And by the way, for those of you who are wondering, why we need to fix things ahead of looking at the data, this might answer some of your questions. So let's compare verification to learning. Okay, so in verification, we have a fixed hypothesis H. Okay, now that's very important. Verification, we have a fixed hypothesis H. In learning, we don't have a fixed hypothesis H. So this hypothesis H is fixed, and when you see the data, all you're doing is verifying H. Okay? You don't get to change H. That was the setup we just described. In the learning setup, the hypothesis is not fixed. The final hypothesis is not fixed because it depends on the data. Okay? So, in learning, you have a fixed hypothesis set H, big H. Okay. And the goal in verification is you produce this H, and I'm going to certify that H is good. That's the goal in verification. But the goal in learning is not to certify the hypothesis set H. It's to certify a particular hypothesis G that is picked from H using the data. So let me emphasize here, the data is only used to certify H. In learning, the data has two uses. That is the complication. So the first thing the data is used for, so you use data to pick G from H. So that's the first thing you use the data for. And then the second thing you use the data for, so here we use the data to certify that H is good. Here we use the data to pick G, and then we have to use the same data, to certify G. So the crucial difference is H does not depend on the data, it's fixed ahead of time. Here, G depends on the data. And that's what's the complication. So in the verification setting, you use the data to compute E in of H. And you don't have any control. You don't have any control over it. In the learning scenario, you can certainly compute E in of G. So you can compute E in of G, but more importantly, the E in of G, the G that you pick will have the smallest E in, the smallest in sample error. It will be the G that looks best. G looks best on data. I.e., you pick G with minimum E in. That means that you control the in-sample error of the final hypothesis G that you wish to certify. You control E in of G. In fact, you're getting it as low as possible, typically, by choosing the best looking hypothesis from your hypothesis set. Okay, now, we can apply Hafting in this scenario. So, we can apply Hafting in this scenario. Let me show you pictorially what this scenario looks like and give you an analogy. So, when we certify, H, we compute E in over which we have no control, and we say that E out of H is approximately E in of H. So that's the applying of Hafting in this scenario. Okay. If we wanted to apply Hafting in this scenario, we would like to make a claim that E out of G, notice the difference. This is a fixed H. This is a G that came out of a picking process, out of a choosing process. We would like to claim that E out of G is approximately equal to E in of G. Okay. And it turns out that because of this fundamental first step where we use the data to pick G, okay, and then, okay, we use the data to certify G. Here we only use the data to certify. Because we're using the data to pick G, you cannot apply Hafting. Okay. Now I'm going to illustrate to you why you cannot apply Hafting. Okay, at an intuitive level, I'll show you what's going on here. Okay, and then I'll show you an example. For example, in medical testing, where if you were to apply Hafting to the G that pops out of here, it would be a disaster. Okay, and it's absolutely important for us to be able to apply Hafting here that the hypothesis was fixed before you look at the data. And that started to give you a hint. Many people ask this question, why does the hypothesis set have to be fixed before you look at the data? And that's because we're going to sort of derive, later on, we're going to sort of modify Hafting, we're going to adapt Hafting so that we will be able to make this conclusion. And just like here, to make the Hafting conclusion here, that we can verify an age, it was important for this guy to be fixed ahead of time. To obtain the Hafting type conclusion here, it will be absolutely critical that the hypothesis set was fixed ahead of time. And if it's not fixed ahead of time, we're allowed to change it at will, and we will never be able to verify that the final hypothesis is good. So let me pictorially illustrate what's going on here. So what's going on here is you have a hypothesis set. Okay, so you have a hypothesis set of hypotheses. Let me call it H1, H2, H3, H4, up to HM. I'm just heuristically listing it as, finite hypothesis set, although most of the popular hypothesis sets are not finite. So each hypothesis set, remember, it reduces to a picture of this form. Each of these hypothesis sets reduces to a picture of this form. Okay. So each of these hypothesis sets can be made analogous to a bin where there's going to be a green region. Okay, there are going to be green regions. Okay. And red regions. Okay. There are going to be green regions and red regions. So each hypothesis has its own out of sample error, its own mu for the bin. Okay. So there's E out 1, E out 2, E out 3, E out 4, and so on, E out N. E out. Each of them has its own out of sample error corresponding to mu1, mu2, mu3. So what is this E out? This E out is a probability that if you randomly generate a point, you end up in the red region. So this is exactly a probability. So it's basically a probability which I could call P1, P2, P3, P4, Pn. Okay. Now what do? You generate a data set. Okay, so you generate a data set. You generate some points. Okay, and it's the same points in each. Okay, and you're going to use these points to evaluate each hypothesis. Each of these gets an E in 1 of H1, E in of H2, E in of H3, E in of H4, and so on, E in of Hn. Okay? But now, here's the key. Okay? And this is the problem. You're going to go and you're going to pick, let's say this guy managed to, let's say this hypothesis managed to separate the green from the red perfectly. So all the data points here were green. So you pick this guy and that guy becomes your G. Okay, so this is what's happening in there. So the data is used to pick this guy because all the data points ended up green here. Okay? And then we would like to now ask the question, is G approximately equal to F? I.e. we would like to certify. And we only have one data set, so we can only certify with that same data set. And the fundamental reason why we cannot apply Hafting is because we are choosing. So we are biasing ourselves towards low E in, okay, and that's occurring because we select the hypothesis. Okay? And that notion of choice comes with a price. And that ability to choose is coming with a price, and that price is exactly the fact that you won't be able to conclude that E in is equal to E out. Okay. Now, let me give you an example to show you, in a sort of a drastic way, why that is the case. So imagine, instead of hypotheses, we had 1,000 monkeys. So monkey 1, that's my drawing of a monkey. Okay, so we have monkey 1, monkey 2, we have monkey 1, monkey 2, and so on. We have 1,000 monkeys, monkey 1,000. Okay, whatever. Funny looking monkeys. Okay, now you want to figure out, which is the smartest monkey. That's sort of like what we're doing here. We have a bunch of hypotheses, and we want to figure out what is the smartest hypothesis with respect to the problem. In other words, which hypothesis has the largest green region. So you want to figure out what the smartest monkey is. But the unfortunate thing is all the monkeys are equally random. So you ask them a question, you ask them an A-B question, and they're going to answer randomly, A or B. That's just the way monkeys are. And so what you do is you administer a 5-question A-B multiple choice test on each monkey. Okay? So you apply a 5-question multiple test, 1, 2, 3, 4, 5 questions, where the answer is either A or B. So, you have A, B, A, B. So each monkey randomly picks either, the left button or the right button saying A or B. So you administer this test to all the monkeys. Well, you must have a lot of spare time. Okay, so each monkey answers the test. And then lo and behold, what you're going to do, okay, is you're going to try to find the monkey which got all the questions right. Okay, so in theory, okay, so perhaps monkey star, here's a monkey star, let's call this guy monkey star, the genius monkey, got all 5 right. All 5 right. Okay, so you say, I have found my monkey that can answer math questions. Okay, this monkey is a genius. This monkey is a genius. Now, what am I doing when I claim that this monkey is a genius? I'm saying that, its in-sample error, its ability to get all 5 questions right, translates to its true intelligence. And that's what I'm saying. I'm saying that the E-in of the monkey star, is approximately equal to E-out of monkey star. But now let's think about this. Okay? Since the monkey answers the questions randomly, there's a 1 in 32 chance that this monkey gets it right. So there's a 1 in 32 chance that this monkey gets it right. Okay? And this is one of the subtle things that creeps in when we move into this world of with high probability. So this is with high probability, right? That's something like a 96% chance that this monkey gets it right. So with high probability, with small probability, this monkey will get everything right. With small probability, this monkey's in-sample error is different from its true intellect. Its true intellect is just random, 0.5. Okay. But there's a small chance, there's a 1 in 32 chance that we're going to think this monkey is a genius. Okay. Even though its true intellect is a 50-50 shot. Okay. And there's a small chance, 1 in 32, that we're going to think this monkey is a genius. And similarly, with each of these monkeys, there's just a very small chance, 1 over 32. Okay. So, any given monkey has a small chance of being considered a genius. But now, because I've given myself 1,000 tries, okay, it's almost a probability 1 that, that some monkey will appear to be a genius because I've given myself many, many trials. And each trial has a small chance of failure. Okay. But sooner or later, one of these trials will work. And we can even compute that probability. You can sit down and compute the probability that, the probability that at least, in fact, the expected number of monkeys which get everything right is approximately 30. So 1,000 over 32. You'll find approximately that many genius monkeys in here. But none of them are geniuses. So somehow E-in for the monkey is not equal to E-out for the monkey. Okay? And of course, I'm not trying to say that our hypotheses are as dumb as monkeys, but the same principle applies. I have a bunch of monkeys. I'm trying to figure out which monkey is the genius monkey. Okay? So I administer a test on each monkey. Okay? And for each monkey, the test will determine almost correctly, or will determine correctly with very high probability whether or not this monkey is a genius. Because I have so many choices, sooner or later one of those monkeys will appear to be a genius, one of those hypotheses will appear to be a true hero, when in fact it's not. And this is basically why of being bound breaks down in comparing E in of G to E out of G. Okay? It's that this notion of choice that I have so many attempts, I have so many chances to con myself that sooner or later I will con myself. And this is something that we are going to have to address if we want to be able to certify the final hypothesis that comes out of learning. Okay. So now let me show you an example of this sort of trap that can arise in medical testing. Okay, so let me show you a cartoon of how this notion of choice enters into this big field of medical testing. So you know, the girl has the hypothesis here that jelly beans cause acne. So is it true or false? And you know, so the boy says, well, I don't know. So let me enlist some scientists, and they go, and the scientists do the correct thing. They get a control group, they get a treated group, and the treated group is given jelly beans. So that's a very happy treated group. And then the scientists do their statistical analysis and say, jelly beans do not cause acne. Okay. And how certain are you that the conclusion of your experiment is correct? So that's the essential question of, does the in sample reach out to the out of sample? So your sample says there's no effect of jelly beans. How certain are you that your conclusion is correct? Okay. And they say, well, 99.5% certain. So there's a 0.5% chance at best that that I'm wrong, or maybe I'm 95% certain. So there's a 5% chance that I'm wrong. But then the girl says, whoa, maybe it's not jelly beans, but it's jelly beans of a specific color that cause acne. Okay, so back to the drawing board for the scientists, and the scientists try all the various colors: purple, brown, pink, blue, teal. They run. In this example, they've run something like 20 experiments. Okay. Now, most of these experiments are saying there's no relationship, but look, we found a link between green jelly beans and acne. Okay. Now, you ask the scientists, how certain are you of each of these experiments? Oh, each of these experiments were 95% certain. So there's only a 5% chance that the conclusion of experiment 1 with purple jelly beans is wrong, and then the conclusion of experiment 2 with brown jelly beans is wrong. Okay, so whatever the conclusions coming out from each of these 20 experiments, it's overwhelmingly likely that the conclusion of each experiment, when looked at independently, is wrong. And I'm going to hone in on this experiment with green jelly beans, which shows the relationship. And there's only a 5% chance it's wrong. Okay, and so it must be the case that green jelly beans cause acne. Okay, and then the manufacturer of green jelly beans goes out of business because we all know what comes next is the headline: oh, green jelly beans linked to acne. Now let's go back here, okay, and let me show you where the notion of choice has corrupted this study. The real question we should be asking here is not, how accurate is each experiment, okay? But the real question is, how accurate is it after we make the choice of which experiment to look at? Okay. So, mathematically, this could be formulated as, what are the chances that, one of these experiments is wrong? Okay. And when you do 20 experiments and each has a 5% chance of being wrong, it's overwhelmingly likely that one of these experiments is wrong, and that could easily be the experiment with the green jelly beans. Okay. So, when you give me the ability to choose the experiment to look at, I shouldn't be looking at, in some sense, the average probability that these experiments are wrong, but I should be looking at what's the probability that I happen to choose the wrong experiment. If I do 20 experiments, one of them is going to be wrong, and that one could be the one that's wrong. Okay. So that's the problem with the analysis. We can't conclude that, green jelly beans are bad. Another way of viewing this is, I'm going to keep doing medical tests. I tested this cancer drug, it failed. I tested this COVID drug, it failed. Okay, I changed the drug a little, I test again, but I get another 10 people. Okay, it failed. I changed the drug a little bit, get another 10 people. It failed. If I keep doing this experiment, okay, eventually, just by randomness, because just by accident, I find a group of 10 people, all of whom the drug worked for, I'm going to conclude eventually that it succeeded. Okay. And that is very similar to this notion of choice. Okay. I'm choosing how long to continue doing experiments, and I'm choosing to stop when my drug succeeds. Okay?
If I really wanted to test, now I need to retest the drug, where I don't have choice, where I fix the drug and go and do another test. And if medical testing occurred that way, you would find far less drugs on the market. Anyway, signing off for now.